Okay, so I'm going to begin the videos again here with section 7.2. Hopefully you guys have already looked at section 7.1. Most of that was reviewed from AP Physics 1 stuff, so not too bad. If you do have any questions over that though, please make sure you let me know. We continue to build on those concepts, and then we do see a lot of new calculus involved in the next few sections here. So please make sure you are through with 7.1 and then ready to roll on 7.2. That being said, we are going to get to this section again. Guys, this chapter is probably the single biggest chapter in terms of new stuff and stuff that is very important for the AP Physics C test. So very important that you understand what's going on. If you don't, you need to be really proactive about coming and letting me know so I can give you guys some extra help. But anyway, let's get to it. So reviewing, right, we know the net force comes from mass times acceleration, and we talked about in the last couple chapters here in the last couple sections torque as well. And torque comes from, right, our force times our radius. So if I bring these all together, right, so if the net torque equals the net force times the net radius, then it really equals mass times acceleration times the radius, where this acceleration would be the acceleration tangent to the circle. But what do we know about the acceleration tangent to the circle? Well, the acceleration tangent to the circle relates to the angular acceleration, right, by the radius times alpha. So if I substitute that in here, I get m times, instead of a, I get r times alpha times another r, or better yet, I get m times r squared and then times alpha, so mr squared alpha. Right, that's supposed to be a squared there. I know not the best, but close enough. Right, so the net torque equals mr squared times alpha. Well, what this does is this actually gives us another definition for the moment of inertia. If I divide both sides by alpha, the alpha obviously cancels out over here, so I get the net torque divided by the angular acceleration alpha equals mr squared, which represents my moment of inertia. So in other words, this is the equation we've seen before, where the moment of inertia equals the net torque divided by alpha, which notice is very similar, right, to the mass, which is the parallel of the moment of inertia, equal to my force divided by acceleration. So we do want to be comfortable with this notion of moment of inertia, right? We do want to make sure we're comfortable with the moment of inertia for an object would be mr squared, and then how can I use that to relate to forces or to masses or whatever I may be using. One of the other big things to remember about the moment of inertia is the fact that the moment of inertia is our angular equivalent of mass. And so what I mean by that is we know that force equals mass times acceleration. In terms of angular motion, we would represent the torque as the angular equivalent of force, and then instead of mass, I'm talking moment of inertia times the angular acceleration. So again, that's the exact same equation I just derived through the force equals mass times acceleration, right? But it is good to think of the moment of inertia as the angular equivalent of our mass, right? So for a specific mass, to find the moment of inertia, it's just that mass times the distance from the center of rotation, and then that distance squared. Right, so we'll look at what happens if it's not a single. So again, this slide here just re-summarizes what I just said. For a single mass, if I ask you to find the moment of inertia, or essentially the angular mass, if you will, right, then all we have to do is take the moment of inertia, which is represented by an I, equal to that mass times radius squared. So if I gave you, for instance, like a pivot point here, and then you had a thin massless string, and you had a ball that had a certain mass, maybe 10 kilograms, located 2 meters from the center of that string. Then if I asked you to find the moment of inertia for this system as that ball rotates around the center there, the moment of inertia would be 10 times that 2 meters squared. Right, so that would be my moment of inertia for this particular object. Well, the question then becomes, what if it's not just a single mass, right? What if it's actually multiple masses or several masses, or even just a few? Right, so let's start with a simple case of that. What if instead of one mass it was two? So maybe I have that same string, but this time I have a ball that's fixed towards the middle, and then another ball that's fixed over here, each of which is 10 kilograms, right? And I asked you to find the moment of inertia for this system if it were rotated about this axis of rotation. Once again, to find the moment of inertia for that system, I would just use mr squared. I would just use mr squared, but I would do it for each of these and then add them up. So the total moment of inertia would equal the moment of inertia of this first one, right, plus the moment of inertia for the second one. So then that obviously leads to the question of, what if there were millions and millions of particles, right? We assumed up above that the string was massless, but what if we have a rod, what if we have a string that isn't massless? right? How in the world am I going to find all of those little particles? Right? If I have a rod, that has some mass, how am I going to find the moment of inertia of those millions and millions of particles and add all of them up? Right? So that's where calculus can come into play to help us out. So if I was trying to do this by hand, the total moment of inertia would again be taking each individual mass, so 1, 2, 3, etc., 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 right? Taking each individual mass times its radius squared and adding all of those up. Right? Which obviously would not be a plausible or possible challenge for us, right? If there's infinitely many particles there, there's no way we can algebraically find the sum. But the good news is, what this is really doing then is we're taking m1r1 squared plus m2r2 squared. We're following that same pattern, right? So we're really just finding the sum of mi ri squared for all I from 1 to however many particles we have, right? So that's what we're doing, is algebraically we're finding the sum of all of those. Well, the reason that's very important is because this ties in with a definition in calculus. Right? When you guys first define the integral in calculus, this is one of the means for which you use the integral to represent. Right? So finding the sum of all of these particles is the same as finding the integral of r squared with respect to dm from 0 to whatever distance we make up. And so that's actually what we're then going to do a lot of in this section. Right? We're not going to algebraically add up millions and millions of particles. That doesn't make any sense. Instead, we're going to use calculus. Right? We're going to use calculus to find our moments of inertia for various objects. So the key definition, the important concept here, the moment of inertia for any object equals the integral from 0 to whatever parameter. So L is often what we'll use if we're using a rod, but we'll see that that parameter does change sometimes. But the integral from 0 to L for r squared dm, right? Where r squared is representing the distance from the center of rotation, so r is representing the distance from the center, from the pivot. And then dm is a very, very important understanding here. dm is representing the change in mass per either little strip or per whatever segment we're taking. So I'm just going to write for right now the change in mass. And you guys will hopefully see what I mean by this in a few examples. But anyway, the moment of inertia we're defining using calculus as the integral of r squared dm. Right? So again, that is a very, very big conclusion for us. We will use this in the next few examples to see a variety of different objects. Okay, so to clarify that equation, let's do some examples that hopefully help you guys see exactly what we're going to have to do. So again, the idea here is the moment of inertia equals the integral. It is a definite integral, meaning it has a specific starting and ending point, which you guys have hopefully seen in calculus at this point. I know BC definitely has, AB probably has as well. Right? But anyway, it's the integral for a definite interval from r squared of r squared dm. Right? So again, breaking this down, we'll see exactly how we use this. So example 1, find the moment of inertia of a thin uniform rod of length L and mass m that rotates about a pivot at one end. So I've got my rod. I've got my rod over here, and then the pivot point is at one end, so I'm just going to say the pivot point is maybe over here. Right? So we want to find the moment of inertia of this rod about this pivot point. And again, if I was trying to do this algebraically, there would be millions and millions of particles along the way. I'd have to add all of those up. Obviously isn't going to happen. Right? So instead, anytime something has mass like this, I have to use calculus. I have to use this integration. Right? So let's break down exactly what everything means. So if I look at this then, okay, so the moment of inertia from the parameters here. Well, if I'm starting at the pivot point, then I'm going to be starting at 0. Right? And then what's the furthest that I get away from 0? What's the furthest distance that I can get out there? Right? The particles that are the furthest away would be the total length, which in this case is L. So from 0 to L, and that's going to be kind of our standard representation, but it's certainly not going to be the only way we look at this. But anyway, so again, that tells me the closest location and then the furthest location away. So then r squared is what I want to do the derivative, or excuse me, the integration with respect to. And then dm represents the change in mass. It represents the change in mass per strip, which we'll see in just a second. So then the problem right now, and the key concept to all of these questions becomes the fact that we want to do the integral of r squared, but right now it's in terms of dm instead of dr. So the key relationship is how can we represent dm, which is representing my change in mass, in terms of dr. So again, let's break down exactly what dm means. So I've got my rod, And then basically what the integral is doing here is we're taking the rod and we're dividing it up into a whole bunch of little infinitely small little strips, right? So we're taking this, we're dividing this up into a whole bunch of infinitely small little strips that go starting from 0 all the way out here to L. So I'm taking, again, infinitely small little strips, adding all of those strips up, and then that would give me the moment of inertia. Okay, so the key with dm is dm represents how much mass per strip is there, right? So if I'm taking these nice small uniform strips, how much mass per strip is there? Well, in order to determine that, let's think about the parameters that we would need, right? So if I want to determine how much mass is in this strip, what are the two things I need to know? Well, one thing that I need to know is what's the linear density, what's the mass per the length of this rod? And so if I look at this question, well, it tells me the total mass is m and the total length is L. So wouldn't the length, the mass per length, just be m over L, right? If I told you that I was looking at 10 centimeters of this rod and I asked you how much mass was in that, wouldn't you just divide this whole thing, mass divided by L, and then multiply that by 10 centimeters to figure out how much mass is in that strip? So the idea is, again, the mass per length is kind of the density. A lot of times they use a lambda to represent that. It's the linear density of the strip. So if I want to know how much mass is in that little strip, I need to take the linear density, I need to take my lambda here, and then multiply it by the width of the strip, which in this case would be dr, right? Because it's a change in my radius, it's a change in how far away from the pivot point am I. So that becomes the key. dm, the amount of mass per strip, is going to be my linear density times dr, times the change in distance of that strip, times the length of that strip, right? If we can boil it down to this every time, it's not too bad. So again, dm in this case would be mass per length times dr. So once I reach this conclusion, finding the integral becomes a pretty easy process, right? So once I reach this conclusion, I'm just going to take this and plug that in for dm. So then let's see what our integral looks like now, right? So now the moment of inertia, my I, equals 0 to L of r squared m over L dr. Now the key concept here becomes the fact that m and L are both constants, right? The mass of the rod and the length of the rod are not changing. So since those are constants, I can go ahead and factor them out. So mass over the length comes out front there, and then I've got 0 to L of r squared dr. And this is hopefully a pretty easy integral to solve, right? This is a pretty easy integral to solve. My moment of inertia equals m over L times the definite integral from 0 to L. And then when I do this integral here, it becomes r to the third power, and then dividing by 3. Right, so r to the third power dividing by 3. I don't have to worry about the plus c because this is a definite integral. Right, so I don't have to worry about the plus c since it's a definite integral, because I'm just going to plug in my starting and my initial and my final parameters, and then find the difference between them. Right, so m over L, and then brackets here. I'm going to plug in the high parameter first, right, the top parameter first, so L cubed over 3 minus my low parameter, which would be obviously 0 cubed over 3, which is just 0. So obviously then the second term in that bracket ends up canceling out since it's just 0, and I end up getting the moment of inertia equals m over L times L cubed over 3, which simplifies down a little bit to ml squared over 3, or better yet, the way that we saw it last year, 1/3 ml squared. Right, so the moment of inertia for a rod pivoted about the end is 1/3 ml squared. So we've seen this defined for us before, but now we can see using calculus exactly where this equation comes from. Right, so last year, if you recall, and if you look ahead in this packet, you actually have this defined in there, but you definitely need to know where this comes from. Okay, so this whole process, this finding the integral, very, very important, something that we do want to make sure we practice a few times. I will in the first part of the notes here, but I will do a few more of these in the next part of the notes. But once again, guys, if this is something you're having trouble with, I know it's difficult to explain without seeing you in person, so if this is something that's not clicking, come find me so I can help you make sense of it.